In today's video, we are going to talk about the beam and some of the theories used in its analysis. A beam is a structural element, generally horizontal or slanting, that is designed to support loads and resist bending. Beams are commonly used in buildings, bridges, and other structures to provide support and stability. The most commonly used shapes for the beams are rectangular and I-shape or H-shape beams, but depending on the specific requirements, other shapes such as circular or T-shape beams may be adopted. Some of the most important functions of the beams include 1. Supporting vertical loads such as the weight of the structure itself, occupants, furniture, and other equipment. 2. Transferring loads from the upper floors or roof to the columns. 3. Providing overall stability of the structure by connecting columns and other structural elements, helping to maintain the structural integrity. Before proceeding, let's first look at some of the supports associated with the beams. A support refers to a component or connection that helps to hold a structure in place, resist external loads, and provide stability. 3 types of support commonly studied are the roller support, pin support, and fixed support. A roller support, which has different representations on paper, is a type of structural support that allows for movement in one direction while providing vertical support, according to the plan of reference. Examples of this support in real life are found in structures like bridges, rolling gates, conveyor systems, and expansion joints where movement due to thermal expansion or other factors needs to be accommodated while maintaining stability. A pin support, also known as a hinged support, is a type of structural support that allows rotation at the connection point. It restricts translation in all directions but allows for rotation. Example of this support in real life includes doors, crane systems, and trusses, where flexibility or movement at the joint is required. A fixed support is a type of structural support that restricts both translation and rotation at the connection point. It provides maximum resistance to movement in all directions, effectively fixing the structure in place. Fixed supports are commonly used in structures where stability and rigidity are essential. Examples of this support in real life includes building foundations, lampposts, and heavy machinery. Having understood those, let's now look at the theories of the beams. Also known as the classical beam theory, it is a model of how beams behave under axial forces and bending. It was developed around 1750 and is still the method that we most often use to analyze the behavior of bending elements. The 2 primary assumptions made by the Bernoulli-Euler beam theory are that plane sections remain plane, and that deformed beam angles or the slopes are small. The plane sections remain plane assumption assumes that any section of a beam that was a flat plane before the beam deforms will remain a flat plane after the beam deforms. This assumption is generally relatively valid for bending beams unless the beam experiences significant shear or torsional stresses relative to the bending stresses. Shear stresses in beams may become large relative to the bending stresses in cases where a beam is very deep and short in length. Based on these assumptions, this beam theory results in the equation of the deflection of the beam, which describes the relationship between the beam's deflection and the applied load. Successive derivatives of this equation can give the expressions of the bending moment and the shear forces of the beam. And integration of the moment equation leads to the expressions of the slope and the deflection, where m is the bending moment and ei the flexural stiffness. Application of this theory led to the development of some of the famous structures such as the Eiffel Tower and the Ferris wheel, and was also crucial to the development of some of the modern methods of structural analysis such as the finite elements method. This theory takes into account shear deformation and rotational bending effects, making it suitable for describing the behavior of thick beams. The resulting equation is of 4th order, but, unlike Euler-Bernoulli beam theory, there is also a 2nd-order partial derivative present. Physically, taking into account the added mechanisms of deformation effectively lowers the stiffness of the beam, while the result is a larger deflection. Here are the bending moment and the shear force expressions for the Timoshenko beam. These are the two most used beam theories for the beam analysis, and they have been used for centuries to analyze pretty much any beam structure known today. An important factor to note is that though the beam is a three-dimensional object, the deformations that occur on the cross-section are considerably small compared to the deformation along the length, such that they can be neglected. This is the reason why a beam, though three-dimensional, can be modeled just as a line representing the neutral axis that passes about the centroid of the cross-section. And that bit brings us to the end of today's video. Please feel free to use the comment section, and if you are not already subscribed, be sure to hit that subscribe button so that you don't miss on the upcoming uploads.